For what?
Yeah, it's collective modes of semi-holographic fermions.
Okay. Holographic semi-fermion.
Yes. So thanks to the organizers. It was great to be in the workshop last week. It was very excellent, and this program still continues to be extremely good. So I'm happy to be here. I will discuss something related to what the talk that Shamit Kalsru gave last week about models where you have Fermi. You want to describe non-Fermi liquids by starting with the Fermi liquid and couple it to some other degrees of freedom. Some bosons, typically gapless bosons, they interact with the fermions, and the interaction make the structure of the Fermi surface different than from an ordinary Fermi liquid. And as Shamit told us last week, it is quite difficult to get some model controllable fixed point purely in field theory. He was describing an epsilon expansion, and you had to use large N expansion. Holography buys us that basically we have a conformal fixed point or some fixed point for the interacting boson theory for free, but we still are going to need some large N expansion. So let me start by reminding of how Fermi surface was first seen in holography by a paper in Liu, McGreevy, and Begg in 2009, I believe, where they considered the probe fermion in the black hole geometry, Reissner, ADS Reissner-Nostrom black hole. So that is ADS4 in the UV, and interpolates to ADS2 times R2 in the IR. And if you consider in general a bulk field that lives in this geometry, say phi, this in the IR can be seen as a field, as a collection of fields labeled by momentum phi k, by momentum in this R2 plane. So like a collection of fields in a 1+1 dimensional dual of ADS2. So it's a local conformal theory, and there is a certain relation between the scaling dimension of the operator in the UV and the effective dimension of the operator in the infrared. This relation basically for a spinor field, for a spin 1/2 field, this doesn't move. This delta is 1/2 plus nu, which is a function of k, with this nu k is given by this formula. It depends on the mass in units of the ADS radius, and then it depends on the momentum and on the charge, if the spinor is charged under the gauge field in ADS. So minus q squared over 2. Can you see, or should I write bigger? It's fine. So you see that this for large enough charge, this conformal dimension wants to become negative, and the fermions want to develop an instability. So you can compute the point function of the corresponding operator, and so the corresponding field in the infrared having this conformal dimension delta will just have a green function which is scaled like omega to the to nu k, and then the full 2-point function is found by a matching procedure, by imposing boundary condition in the UV and then interpolating the solution in the UV and the IR. One finds that the full Green's function has a form like where this curly G is the infrared correlator, and the A, B, C, D are analytic function of the momenta and the frequency. And so if it so happens that this has at 0, it's a certain finite momentum, so if C of k omega happens to be 0 for omega equals 0, and for a finite k, then you will have a pole for this correlator, but with a non-trivial exponent. So the Green's function then will have the form of a Fermi liquid, but with the correction, this curly G plays the role of the self-energy, and the self-energy will be different because in a Fermi liquid here you will have instead of G, you will have this sigma is omega squared. Is the first correction to the propagator between interactions, and this squared is replaced here by some non-trivial scaling exponent to nu. So and this Z is also a function of omega and k, which is the residue of the pole, and tells you about the renormalization of the quasi-particle, or the overlap of the quasi-particle to the free electron at the Fermi surface. And then Polchinski and Faulkner argue that this essential part of this physics can be captured in a simple model, because essentially you can think of these fermions as living at the boundary or in the domain wall between the ADS4 and the ADS2 region. And the essential physics has to do with the IR part, so you can forget about the UV and having a complete theory, and you can replace this model by just some fermions that live at the boundary of the infrared geometry, and then you still need the infrared geometry to account for the strongly coupled degrees of freedom. And this leads to this semi-holographic model that was introduced by Polchinski and Faulkner. Which is considering an action that has some free fermions with the usual kinetic term, and then they are coupled quadratically to a psi, which is an operator in the conformal field theory, and this psi has a dynamics which is given by the bulk action, which is the action of in ADS or the infrared geometry. Let's call it test of the CFT. So you couple quadratically this guy to a strongly coupled fermion, and this is a bit different from the models of Kachru, where the coupling was typically some quadratic bilinear times a boson, an order parameter, for example. But okay, it's morally the same story. And then if you work in the large n limit, this boson is a free, this psi is a free field in the bulk, so the whole Lagrangian is a free theory. You can still diagonalize and find the propagator for this guy, and this chi propagator is the same expression that I wrote there for the non-Fermi liquid. So this gives a nice model to study, to investigate the phenomenology of this class of non-Fermi liquids that you get in holography. And they argued, moreover, that this fixed point is stable, at least at large n. The reason is that if in the situation where ADS2, the infrared geometry is exactly ADS2, then this field, this chi, here it's so the Fourier transform. I'm using a real coordinate representation for time and then momentum for chi. This chi has dimension 0, so because there is a field of dimension 0, there is a lot of relevant deformation that you can add to this model in principle. But if you look at all this deformation, it turns out that most of them do not actually perturb this fixed point. Yeah, although it's a non-Fermi. Right. So one should notice, okay, this statement it requires some elaboration to be made more precisely, because actually what happens if you add, there could be a relevant coupling of the form. So this coupling is relevant, of course, but it we already consider it as part of the Lagrangian. If we change its if we deform it, change the coefficient, then in some sense the fixed point will change, but it will be just another fixed point with the same low energy physics. It's just like rescaling mu in the Fermi liquid, just moves the Fermi surface, but otherwise all the physics is unchanged around the new Fermi surface. Most worrying the deformation is one of the form psi dagger psi. But this is a double trace deformation in the field theory, and so its effect can be studied easily in the large N expansion. We know that this double trace deformation just induces a flow that changes the quantization of the field. So this deformation is relevant if the dimension of the operator is less than 1/2. But in this region, this psi admits an alternative quantization where you exchange the Neumann and the Dirichlet boundary conditions in the infrared, and adding this deformation flows to another theory where the psi now has acquired a conformal dimension which is bigger than 1/2, and so this perturbation has become irrelevant. So basically this perturbation also is not dangerous, it just tells you that you never need to consider operators with this conformal dimension. And then most of the other deformations, relevant deformations that you can write, are also similarly mild in the large N expansion. Okay, this is more or less where they left it, and one can still observe that this model allows one more freedom with respect to a fully holographic construction, in the sense that one can easily include, for example, effects of the lattice by just requiring K to live in a lattice instead of in a continuum, and so on. So this was as introduction.
Sorry, one question.
Yeah.
I didn't understand. So this type of model then was solved with ADS techniques, or was solved by conformal field theory techniques? This model.
This model is a free model.
No,
So
but the question is that first, how is this related to ADS?
Yeah, this ADS is contained in this part.
Yeah.
So this part is some conformal field theory that you are supposed to know, and this, yeah. So for that you need ADS to. But at this level, we just use the two-point function of these operators which appear in the theory. So.
And so the crucial part is that these fermions living in front of isolate, the label are in weak correspondences about it, right? And then you read off from the dot geometry that these things can tunnel to the deep infrared, right? And that's basically written there.
Yeah, you check out.
Or then you basically get to see there the marginal firm liquid theory where you just do second order perturbation theory for all first corrections, and now you're legal because first corrections are one of them suppressed.
Right. Also, one could mention that this picture can somehow be put in correspondence with the idea of the fractionalization of the electron. If you can see, if you see this, this chi as the UV electron, and then in the full theory is the mixing of the electron with the infrared degrees of freedom. You can see that the renormalized electron somehow is fractionalized in the sense that it mixes with an operator that with some other fermionic operator, if you want. So depending on the model, okay, this can be made more precise or not, in the sense that this fractionalized electron can have a fraction of the charge or different quantum numbers than the original one. So next we would like to understand what in this model goes beyond the physics of free. So we want to turn this into an interactive model and study in particular the collective modes. So the zero sound, which we heard in last talk, is one of the most distinctive features of the Landau Fermi liquid, and we try to understand maybe I'll start here. How it is modified in this case. So so first of all, we need to generalize the Porczynski-Faulkner model to allow for interactions. And so okay, we start with the same quadratic action, and we can have interactions of the form well, there are basically interactions between the fermions and the conformal field theory. So this can have this can be trilinear coupling with a boson, say phi, or quadrilinear coupling with another fermion. Or there can be self-interactions of the free boson. So things like Heidegger chi squared. And here it's convenient to separate the possible Coulomb interaction, or generically some long-range interaction. So this is momentum k plus q k, and then k prime minus q k. So we assume that there is some short-range interaction where the coefficient is not a singular function of the momentum, and this vq, which will typically be 1 over q squared or some other power, because this v can also get contributions from the exchange of bosons in the conformal field theory, which could lead to exponents like q to alpha with alpha less than 1 generically, so something milder than a Coulomb interaction. Okay, and this model is not solvable generically, but we can control it. So we need to use some large n expansion. So we know that we need an n squared here, and actually this interaction also needs to be considered of order n in order to have a leading effect on the propagator. So this interaction needs to modify the chi-chi propagator to order 1. With this n squared here, you need this to be of order n. So this is easy to see because there is the propagator will be affected by this, where here there is the psi propagating, and because the psi propagator is of order 1 over n squared, you need the interaction vertex to be n, so that this correction is of order 1, and after you resum it, you go from the free chi propagator to this corrected non-Fermi liquid form. So this fixes this power counting here, and actually this extends to all the interactions. So every interaction of the free field with the conformal field theory operator has to come with the power of n, and then we add an n also here and here, but not in the self-interaction. So basically the idea is that there is one fermion, if you want, and interacts with n fermions of the conformal field theory, and there can be other scalars. So so it would be interesting to see how this matches with what Katsuru was saying last week, that he has this line of fixed points parameterized by the ratio of nf over nc, the number of bosons, the number of colors, so the number of bosons divided by the number of flavors, so fermions, and it seems that in our model this ratio is n squared over n, so it should correspond to one particular direction in his diagram, but I haven't yet seen how the two compare.
So there's a tool is like n limit here is in first instance that you ignore all these first corrections associated with the first line of your action, right? And these first corrections are perhaps of the same order as the fermion interaction you explicitly treat. I guess nobody really knows how to treat these kind of first corrections. I know that's the approximation or something.
But anyway,
that's a sort of in the condensed context, it's sort of interesting history. The first line is just like the marginal fermion liquid. There's three fermions, and there's a conjugated column medium out there, and just doing a second order perturbation theory job between the two. And shortly after that was published some good diagram. Douglas came up with a proof that actually it means that the first function has to be singular. So it cannot be possibly a consistent construction. Here you say, okay, it makes like n that saves my skin from it, but you start to worry about 1 over n, you perhaps have to really forget about that problem.
I see. Okay, thanks.
Yeah, you have this same problem here. If you don't put the n factors. Yeah.
So what's the space-time dimension?
This 2 plus 1. Well, it could be done for other dimensions, but
And chi and phi are just one field.
so chi is one field.
Phi is also one.
This phi?
Yeah, the boson. Yeah.
Okay, the boson. Well, I assume there is a lowest dimension operator that should be the leading contribution.
And what's the dynamics of phi?
Phi is a some primary operator in the CFT, so it has.
That is included in SCFT.
Yeah. But actually, we argue that in the end this coupling only contribute. They do not affect really the analysis that I will make. Basically, they give some finite correction to the vertices. But okay, let me go on, and I will. It will be more precise what I want to say. And what we want to calculate is the response function. So how the system responds to an external perturbation. So typically, you want to excite. These are charged objects. You perturb them with an electric field. So you need to add some coupling. The external coupling will be so a coupling to an external gauge field. And then, given the n counting rules that we have adopted, it is natural to assume that this gauge field couples to the current of the free fermion with 1, but with an n squared to j mu, which is some current in the U1 in the CFT. Sorry. And now here we need to make actually another assumption that the J mu, the current in the CFT, admits an expansion in terms of sum of operators, in terms of the charge, say, and delta. So almost like if this over free fields, I mean, in some sense we know that CFT is dual to ADS, can be in many sense treated as consisting of generalized free fields. So I think at least in this class of models it is not, or I don't know if it is even possible to prove it in general that the current can always be expressed as an expansion in of course, renormalized composite operators of this kind, summing over the basis of all the charged fields. I think it's quite plausible, but I don't know the proof. So if this is true, then this tells you that basically also this current is bilinear in the fields, in the bulk fields as well. And then we can use a diagrammatic expansion to compute this response, which takes this form. Basically, we insert an external current. This couples to a fermion bilinear.
So that imply I guess there's some matrix in the middle which accounts for the Lorentz.
Oh, here?
Yeah.
Right, yeah.
And then the other thing is, I guess you introduce an extra symmetry if you do that.
Why?
Well, you can rotate each of the O and, if you put a face to each of them, they will cancel.
It's not an extra, I mean, it's the same symmetry, no? I mean, also here, this is the current, it's a U1 current, so it's gauge value. So if I rotate the fermion with the face, it's invariant.
Yeah, sure, but you get more symmetry than you had before.
I mean, I'm assuming that there is some symmetry, otherwise I cannot. Yeah, I have to assume that the symmetry exists. But basically, I kind of already assumed it here. I mean, this coupling only makes sense if this psi has the same charge as chi. Otherwise, I would have to do something different. So I measured the response of this perturbation, and here I have the density operator, the density of fermions, which has a contribution both from chi and from psi. But in the end, it will only depend on the renormalized field, which results from resumming this, which can be written as chi tilde if you want, this chi, and it mixes to 1 over n order with the, and the other is the. So this is the diagonalization of the propagator to leading order, and we compute the n of this chi tilde field by this expansion, and then there are corrections that are expressed in this way, and there is this box, which is basically the resummation of the 4-point function, which you compute by resummation procedure, which is called the Bethe-Salpeter equation, where this is so in a diagrammatic expansion, it's easy to prove this relation. If you define this to be the two-particle irreducible contribution, so the sum of all diagrams that cannot be disconnected by cutting off two lines. So this is similar to what you do normally for the propagator and the one-particle irreducible part, but here it's the two-particle irreducible. So and you have to separate off the part which has two disconnected lines. Now if I put momenta labels, this is k plus q, k prime plus q k prime. So this is a diagram with the momentum transfer q, and q is also the momentum transfer in the internal lines. And now, So this equation, this is schematically a representation of an equation that tells you that n can be expressed in terms of Q times E. So E is the applied electric field, and Q is this propagator. And actually, it's enough to consider the singular part of these two propagators. Sorry, this is E tilde, and E tilde is the correction, is the applied electric field renormalized by this diagram, by this box, if you want. And this is an expression. It satisfies also an equation that has the form. Let me write it down. And here the Landau parameters make their appearance, but in this context they can be defined precisely. They don't have to be introduced phenomenologically. One can see that this f is actually nothing but the limit of gamma. Sorry, I call this fourth point function gamma tilde. No, gamma. Sorry. And gamma tilde is the two-particle irreducible part. So the equation has the form gamma is equal gamma tilde plus gamma, two propagators, gamma tilde, and all these products are integrals of momenta and matrix summation over indices and so on. All of this is implicit. So it's an integral equation, and basically this integration for gamma implies a similar equation for the applied electric field. It's essentially the same equation. Yeah.
So here, can you ignore the back reaction of chi to the CFT sector?
What are you, sorry?
Can you ignore the back reaction of chi sector to CFT?
Yeah, okay, I'm working in this assumption. So this.
But in your action, that seems to be order of n square.
No, that's n squared is the action of the CFT.
If you consider self-energy of phi, say bubble diagram of the phi, mediated by bubble of psi, bubble of chi, will generate some Landau damping for phi, which is order of n squared.
The
Particle Hall extensions of chi will generate Landau damping for phi, which is order of n squared.
So yeah, that's right. But in the end, this can be reabsorbed in this function. So that's the basic point. But our main contribution will come from this propagator only. So what this gamma tilde can be affected by all sorts of corrections, but it's not crucial to.
This is a fairly good question, right? So there's just a standard law of electron stars, etc., right? And they basically assert that in this order, right, the fermion matter has to back react on the metric. Right, there is a highly non-perturbative business, right, where you completely blow away the deep infrared, you get Alicia's whatever. And that you cannot describe in any way doing this perturbative business, right, because you really don't affect the deep infrared in this way.
But this.
In the electron star itself, you pay some attention to interactions, and you say.
Yeah, for the electron star.
Contributions also to the real field.
Yes. So if you fully account for the back reaction, then I agree that this wouldn't work anymore.
So just from field theory point of view, the propagator of phi field should be modified by back reaction of chi.
It will be modified for sure, but in this diagram you never see the propagator of phi. It doesn't become singular at the same point.
You're throwing it out by hand. You're completely frozen in the CFT. And it's just a spectator all the time dressing these fermions. And the back reaction is telling that the fermions change the SCFT big time in a very non-perturbative fashion. And I don't think that you can capture that in perturbative diagrammatic theory of any kind. Because SCFT is very non-perturbative stuff. And the way it turns, it really changes into a stable thing is also very non-perturbative. So you can again say, okay, I ignored it, right?
Yeah,
Separate small parameters to control it. That's what they say.
This needs to be looked more carefully. What happens to the bosons in this case? But yeah, in any case, I don't think that if you want to describe the full effective theory for all the excitations, yeah, what I'm saying may not be exactly true. But for this
Also, the detachment, right, is the systemic condensed matter setup of your whole critical field. It's a very standard critical boson, right?
Mm-hmm.
Which is very, very different from this ADS2 type quantum critical state, semi-local quantum critical state. There's really no two other to describe that, you know, explicitly in field theoretical language that we understand. But it's about ambition, and you said I don't quite have the ambition to have a literal connection to the mainstream to the critical bosons.
Right. Yeah. Okay, but okay, we can discuss later this point if you like, because basically here the point is that what for this argument what you need to consider is the correction to the fermion propagator, and the self-energy correction. One can see is actually that with respect to this three-level correction, they will be subleading at low energies. So the main contribution comes from when you have two fermion propagators renormalized, but they will have the same form that I described before. And the singularity comes from when they become when both these lines can be simultaneously on the Fermi surface.
I don't think it's subleading, because you need to know the fermion propagator, and in the fermion propagator, the phi propagator and psi propagator enter as a safe energy. And then if this phi field and psi fields are modified to the leading...
No, I'm not saying that it's subleading now in large N. In the large N they will contribute, but for this particular, I'm considering now the case where omega, so I wrote the infrared part of the correlator was going like omega to the nu, and I'm interested in the case where this nu is now something between 0 and 1, because this will correspond to, for nu bigger than 1, this correction will be subdominant with respect to the omega which exists on the around. I mean, there is an omega coming from the free part and an omega nu coming from this part. We are interested in the non-Fermi liquid case, which is where omega nu is dominant, right? So we can ignore this term, and then this requires this condition, and this remains satisfied in perturbation theory.
You can.
Okay. Yeah. Okay, I have some time still. So the way it worked in the normal Fermi liquid case, one derivation that you can give for the zero sound is that you start from the again from the normal Fermi liquid, free Fermi liquid propagator. In this argument, we need the Feynman propagator, so we need to consider an I epsilon prescription, and the right I epsilon prescription is to take different sign according to if you are just outside or just inside the Fermi phase surface. So this gives the Feynman propagator. And so with the property that the poles are in the upper half plane for k Fermi, so this is the k parallel is the distance from the Fermi surface, and in the lower half plane for negative. And also it coincides with the retarded one or the advanced one, depending on the sign of omega. So when you consider a product of two Green's functions and you integrate over omega, at some given k, and you do the integral by doing some contour in the complex plane. So this will be at some momentum k plus q and k. So there is a propagator that depends on k plus q parallel, and another which depends on k parallel. And of course, this can now have poles depending on q. The configuration of the poles can change. So if you have two poles inside the contour, in this case the residues cancel and you get 0. If they are both outsides, of course you get 0, and you get contributions only if one is outside and one is inside. So this will be proportional to theta k plus q, theta minus k. And if you expand for small q, that basically gives you a delta of k. So the integral gets contribution only from exactly the Fermi surface, and so in the limit q goes to 0. Then you can find that the q, if you want the singular part of the product of GG, then it has to be proportional to delta, and the coefficient you can compute by performing the integral, and it turns out to be so this is j of k plus q and frequency omega plus big omega, and this frequency omega. So small q and big omega are the frequencies of the exchanged mode. And from this form you can then plug it in the equation for the fluctuations. In this equation, if you set E equal to 0, because you want a mode which is self-sustained, a normal mode, so that it exists without any external perturbation, then basically you see that you can rewrite the second equation as something like q minus 1 n, because n is q E tilde, so E tilde is q minus 1 n is equal to integral of f times n. And basically, with this form of q, you recover the Landau, the equation that Andrei wrote in the last talk, which is so this is the equation for the collective mode n, which describes the zero sound, and I will not elaborate here because Andrei already discuss the solution and the meaning of the f parameters in this case. So we want to parallel now this discussion for the non-Fermi liquid case. So what changes, of course, is now this Green's function has the form omega to the nu. So we need to be a bit more precise. This omega to the nu actually comes with the complex coefficient in front. So let me rewrite it. There is a g omega to the nu minus k hat, and this g can be written as a real number times a phase. And now it's quite important to know that this phase cannot be arbitrary, at least in the model that in the form that was found by McGreevy, Liu and company. One can prove that for a spinor in ADS, this phase is bounded by pi times nu minus 1. So without this restriction, it becomes more complicated, because this basically puts the poles of the Green's function in the right place. That is, for the retarded Green's function in the lower half plane. And then
That's some kind of Policastro argument.
yeah, probably. I mean, yeah, one can. So yeah, indeed, we will assume that this is always true. And then this allows to write the like in the normal Fermi liquid case, we need to promote this to a Feynman's Green's function with an I epsilon prescription. So we say that the right prescription here is to take now the sigma of the sign of the Fermi momentum goes in this phase. So one can show that this is it satisfies the right properties of having the poles in the right place. And now what happens when you do the integral of 2 Green's function? This is a function of omega to the nu. So you want to map it to the z plane, which is omega to the nu. And so this plane becomes the upper half plane of omega becomes a wedge of width pi nu in the z plane, and then there is a branch cut because it's an analytic function, but you can place the branch cut along the negative imaginary axis, and then if you do the contour in this way, you see that you never are going to get contributions from the branch cut. So this part was missing from the time I gave the talk in Leiden. We didn't quite realize how to do this. Yeah, and then you can do the integral. So now the difference with the ordinary Fermi liquid is that you don't get contributions only from when the poles are outside and inside. Basically, because of the non-trivial structure of the correlator, the residues don't cancel. When you have 2 poles inside, the residues don't cancel and you still get a contribution. So you get something. The Q function will now go like theta of k and theta k plus q. And then it doesn't reduce to a delta function anymore. So it, so let me write it down. This is okay. If you do the computation, you get something with these 2 thetas, and then there is a factor. Is 1 over this coefficient that I wrote there. So okay, can you read?
It's exponents of k perpendicular.
1 minus 1 over nu.
1 minus
1 over nu.
1 minus 2 divided by nu.
1 minus nu over nu.
And the other one is
Omega hat.
the other that k parallel in front of it. There's an exponent
Here.
parallel. Oh, yeah, there, right?
Here is 1 minus 2 nu over nu.
Yeah, and there it is.
1 minus 1 over nu.
Okay.
Yeah, it's different.
Yeah.
So this q hat and omega hat are just momenta rescaled by g. So and then the non-trivial difference from Fermi liquid is this function of k perpendicular or parallel that appears with different powers. And then this, if you want to find the zero sounds, you still actually have to integrate over k over the momentum, and you find an equation. You find an equation for the velocity, which I can write here. So now I solve it in the simplified case where the f parameters is isotropic, so there is only an f0. So you get an equation. It's now a much more complicated equation. It's a transcendental equation for V0, and then there is Vf over d squared. So this, and V0 here is the zero sound defined as omega over q. So one finds that there is a solution in when omega is proportional to q, like in the ordinary case, and the velocity satisfies this equation. Okay, so now one can check that in the limit nu goes to 2, one gets the right Fermi liquid. It reduces to the Fermi liquid case, and otherwise it's something non-trivial. So what do we do with this if we want to compare this with some experiment? What does it depend on? It depends on f0. So in the limit of large f0, this goes actually like g to the minus 3 over 2 nu. So the square root of f0 is the same like in Fermi liquid, up to prefactors, which depends on this case c, which is a cutoff on the momentum integral.
How do you see the mu equal 2 is a special?
It's not special. It's
It's not Fermi liquid exponent.
It's supposed to be the Fermi liquid case.
Not from your equation.
Well, you have to expand and take the limit. It's not. If you do it with Mathematica, it's.
It might be G is what?
Okay, G is written here.
Oh yeah, that's the phase. Wait.
So this is up to non-universal prefactor.
G is just the phase angle, and I guess you have to take that absolute.
No, it's not just the base. There is an H.
An H, yeah, but so it's a complex quantity. So V naught is complex at this point.
Yeah, we know this complex.
Yeah.
So
Now you really make your part. Oh, you know, if you spot at gamma.
Right,
phase
right.
factor, yeah.
so what you
So
can.
it's generically damped or undamped. The real part of V naught larger or smaller than the imaginary part. That's the important one, right?
Yeah, that depends on nu, right?
Yeah, so when you exhaust nu, that's like nu going to zero, right? That is the most extreme case.
So if you want mu goes to 0, so this is e to the minus 3 over 2 mu gamma. And gamma will be, as I said, is bounded from 0 to mu minus 1. So this goes from being real to being e to the over 2 nu. What is this thing? Well, it can be actually anything, I think.
Oh, you just click out. So the marginal vergelijkelijkheidsnu is 1, right?
Nu equal 1.
Yeah, so it's 1 minus 1 is 0, so it's purely real.
Okay.
And when nu is 0 is the most extreme case. And then it seems to
It seems to be very
meaning
how so you cannot go easily to nu equal 0 in this.
So it's e to the minus I times the 30. Oops, so what is going on there? Would be prejudice at some point the zero sum gets overdamped, right? And you get too small.
Yeah, well, this starts oscillating a lot, so it's, I would say the limit nu close to 1 is more sensible. And but it depends on this gamma. So somehow this it's an information that we put in. It's not simply, but okay, this predicts at least that the damping, or the ratio of the damping to the velocity, will be something that you can calculate in a given model, whereas other features can be cutoff dependent and cannot probably be compared to experiments. And the last thing you can do is, I didn't mention this before, but if you want to, this was for the case where only the f parameters were important, which means then the interaction was short-ranged. If you now have long-ranged interaction, you have to replace f in the equations by f plus VOQ, and for small q, I mean for singular, yeah, for small q, the singular contribution of v will overwhelm the contribution of Landau, so v is with 0 over q squared, and then you cannot use this assumption anymore. You have to, yeah, if you replace in this equation with 0 is omega over q, and f0 goes into v0 over q squared, and you expand for small q, you find that there is no more a zero sound, but there is so the solution has an omega at 0.
That's a plasmon.
That's normally the plasmon, but in this case also becomes complex. And you get an equation for the plasma, which is V0 times g to the 6. So again, with some complex frequency, which is governed by this constant g to this exponent.
So at q going to 0, you still have the damping of the plasma, right? Or purely real, actually.
Yeah. Okay, in this case I'm not sure you can easily see take the limit, because there are some prefactors which I ignored. Yeah. Yeah, I'm done. Thank you.
Before people ask a question, could you just summarize in pure words what is your conclusion?
Okay, the conclusion is that in this class of models, you can calculate the properties of this collective excitation, the zero sound. It has some similarities with the normal Fermi liquids, but also some differences. It will be typically damped always, so the damping can be more or less compared to the real part. So, but Also, it typically does not seem to admit an interpretation as a particle Hall excitation, as it gets contribution from excitations which are both inside the Fermi surface, for reasons that we don't really understand.
It's called particle physics.
Yeah, yeah.
Everything.
And for relax.
And let me also mention that one can use a similar analysis to study the BCS instability, which we haven't done yet, but it can quite easily be done with the same techniques.
Thank you. And now question.
I would like to sit together with Giuseppe and further analyze it.
Sorry?
I would like to sit together with Giuseppe and further analyze the expression.
Yeah, nice.
So if no question, then let's thank the speaker again.